section, 7.1. 7.2 is it slightly more advanced techniques of integration. So integration technique you see in calculus is substitution method, what we're about to learn, and after that you learn integration by parts, and thirdly you learn slightly more different direction of the substitution. It'll surprise you that it's the same thing, but it's opposite direction. It's a surprising result. And combining all together, and you're going to enter this partial fraction decomposition. It's a very lengthy calculation, but it involves all previous one. So first one is a substitution method, and here it says integrating chain rule. The result of a chain rule leads to the substitution method. How did we actually integrate in the 7.1? Was just differentiating and doing the backward, right? You look at the elementary basic function and differentiate it, and then the backward, that was in basically the method. So this time we are going to apply the chain rule to our basic functions and think about how to reverse the procedure of a chain rule, and that method is called the substitution method. So substitution method is reverse of which differentiation rule? Chain rule. Right, so we're going to look at chain rule and see how it works. And here is some examples of a chain rule. And you know how to apply the chain rule probably. However, in my experience, not many students actually remember its correct abstract version. Many students actually end up at just doing this example and that example and just know how to handle the chain rule of the various different examples. So here's a slightly more abstract version that I think is important for you to understand this method, and later on in Calculus 3 this is also very important when you enter multivariable chain rules. So y is here this function x squared plus 3 raised to 7th power. If you think about order of operation to compute this one, it involves several operations, but you can divide it into always two groups. First you calculate x squared plus 3 first and raise to 7th power, right? So when you split into two different operations like that, understanding the order correctly, they usually make this substitution, u substitution. U is going to be the first thing you compute, x cubed plus x squared plus 3. Then y is simply described as a u to the 7th. And then you understand u there is actually a function of x, and this is how you write it. Okay? Then this thing here you wrote is simply dy dx, right? Y is a function of x, differentiating with respect to x, correct? But this can be written like this. This whole thing is actually written in terms of u, so it's a u to the 7th power, where u is in terms of x, correct? So following is incomplete, but if this derivative is u to the 7th is done with respect to the letter u, the answer of this one would be simple, right? 7 times u to the 6th. But that's not what you have down there, dx, not du. So these two things are not equal to each other, right? Then you have to multiply one factor, and that makes a chain rule. This variable is going to chain together. Du down there and du appears up there, and dx was down there originally. Now it appears under the du. So you're allowed to do that, and what is this rule called? Chain rule. This is simple substitution. There's no chain rule here. And to explain why is these two things equal, that is the theorem called the chain rule. Okay, so you're allowed to do that. I explain in my Calculus 1 course using the delta delta y divided by delta x. That's not dx dy, right? It's a limit of this one is a du dy. So you can understand things more naturally using this delta. These are actual quantities. Then you can actually write it like this: delta u, delta y, delta u times delta u divided by delta x. This is easy to understand why that's correct. If you start with the right hand side, cancel the arriving left hand side, that's easier to understand. This is dy du, which is what you're looking at here, and du dx, that's what you're looking at there. It's a simple explanation through the delta notation. Make sense? So what is the answer to this one? if you differentiate this one with respect to u, that's 7 times u to the 6th, right? But you have to multiply your u and its derivative with respect to x. What is the derivative of this one? 2x, right? With respect to x. Then you substitute back 7 times what was u? X squared plus 3 raised to 6th power times 2x. Right? Now, so that's the chain rule. Expanded with the full detail. So what's the idea behind it? Even explained using this delta notation. Our goal is reversing this one, right? So let me write that down. Over here. I think this version I like. This is a specific example, but in general, you have something like this written in terms of u, then multiplied by du dx. They're all simplified and hidden, so you don't see this structure. But it is this by looking at this expression, it is actually in that shape. But if I further expand this one or simplify, you don't see this nice structure. From that point, you want to reverse this one from here to there. It's no longer equal. So how am I going to get from here to... this is the answer we want to find, right? Is u to the 7th. That's where we get to. This is where you start. I give you this function. I ask you to find the antiderivative. And you don't know this structure. You only know this explicit information. So what procedure do we have to do to this thing to get to this x squared plus 3 to the 7th power? First thing is that I'd like to get rid of this du dx. Get rid of that, and what do you have? Du u to the 7, right? You get rid of that and integrate this one with respect to u, right? So I'm going to write it like this, integrating maybe the stars. Whatever you have it there with respect to u, then you will arrive at here u to the 7th, right? Because you differentiate with respect to u and integrate it back in this, going back to that. So that's our answer, plus c. This is our goal. It's easy to say to get rid of it and integrate it like that, right? So you have to write it as a more of a procedure, the correct arithmetic or algebraic procedure. So first of all, by looking at this expression, and here, this is the expression you're looking at, right? You have to choose u. That's the hardest part. You have to practice a lot so that your decision making on what my u is going to be is getting better and better. But at the beginning, you will go through a little bit of a trial and error period. But I guarantee you, as you practice more, this is going to be doable. Now, I want you to look at here. Pretend don't know what happened in here. I want you to look at the expression and figure out what our u has to be. And if you don't know anything about it, then there's no you have no clue to what my u should be. But here's usually what should be happening. If you decided, just go ahead and choose it randomly. I'm going to choose 3 to be my u. Then what is my du dx? 3 is my u, then du dx is 0, right? That's not good. If I choose x squared plus 3, that's my u. Then du dx is 2x, right? And you see, oh, there's a 2x out there. You kind of see that it's du dx out there. You realize that a little bit of a structure in there. That's how you make a decision in u. My u is going to be x squared plus 3 because I see its derivative 2x out there. If you don't see this 2, it's still a good sign. The constant multiple is not an obstacle problem in this procedure. So you make that choice du u, and then in your mind, or you usually have to write it down, compute this du dx, and that's available, right? So you make that choice of u and compute du dx. So with that much of a calculated, what should I do? Go from here to there. What operation should I do to get rid of du dx? Is multiply by what factor? Du dx reciprocal, don't you think? If I multiply reciprocal of du dx, I ended up at canceling this one, end up at exactly here, right? Now you already made a decision in u. So if you could write this one all in terms of u, then you can integrate it with respect to u. That's not hard, right? Okay, so you multiply du dx as reciprocal, and whatever is left out here, you have to write it all in terms of u before you integrate with respect to u. Then whatever you have at the end is going to be answered in terms of u. Then you have to substitute back with what your ux is in terms of x plus c. That's the idea. Okay, I'm going to summarize this one very in a few lines. So let me grab this one. Not much of a description. Let's see if this thing makes sense. First, this is given. This is all you have. Integrate this function or calculate this indefinite integral. So you are looking at some expressions inside the dx, and you have to make your choice on u equals something h of x in there, or just ux in there. Then you're going to multiply the reciprocal of du dx. Remember why we're doing that? So, purely in terms of u. Then you notice here that your dx is changed to du. I want you to be very clear in this switch. This is a theorem, right? You are given a dx integral. Now you can switch to du integral by switching it like this, right? Without the du in there, dx, this is not equal, right? If it is same dx and dx, how can this be two things equal if the integrand function is completely different? We have additional factor. As soon as you throw in this factor, which we call Jacobian factor, that's the official name for that, and this appears in calculus 3 as well, this type of phenomena. If you multiply that, you switch to du. Now you have to simplify and rewrite this one all in terms of u before you actually integrate. So I'm going to look for your correct transition in here and correctly using the integral variable. If you use it incorrectly, there's a deduction of 10 points. This is really showing how you are thinking this procedure and understanding where to where is a theorem, where to where is a simple algebra. All right? So this is a theorem part. This is non-trivial part. Okay? Dx integral switch to du. Now, this one is all in terms of u. Just look at this expression in u and integrate it with respect to u. Then you get something in terms of u. Then you substitute back what that u was in terms of x, and that's the final answer. All right? So I'm going to show you in a little example. If I have to integrate x squared plus 3 raised to 7th power dx, excuse me, and there's this x out there, dx. Okay? What is the first thing you have to do? You have to make a choice of u. Then underneath it, you're going to write it, what's going to be my u, right? So what was a good choice? Cheating a little bit of what happened before with this similar looking function. Yeah, x squared plus 3. Then you immediately calculate in your head or on paper like this. What is my du dx then? 2x, correct? This one differentiated 2x. Now from here you make a little bit of decision that my choice is good. Why is this my choice of u is good? Because 2x is out there except 2, right? Except the constant multiple 2. So it's good. It's going to kind of cancel it out as you multiply the reciprocal. Remember? So from here is a theorem. Integral switches to what variable? du. Please note that we're switching to du. You keep everything here. X squared plus 3 to the 7th power x. That's what's in the function, right? F of x. Now what are we multiplying here? Reciprocal of what you have just calculated. What is reciprocal? 1 over 2x. All right? That's how you enter the du integral from dx. That is called substitution method. Next goal is that you have to write this one in u. That's this next procedure. Okay? So first of all, you see the cancellation of x there? That's why we're actually doing this substitution. And what's left here is 1/2. There's a constant multiple that goes outside. Is that right? Fair enough? Then what's left? X squared plus 3, the 7th du, right? But what is this one in here? All in terms of u is simply u to the 7th. So let me rewrite it. F and here u to the 7 there. This is a simple algebra, right? Simple algebra. I didn't do any calculus or anything. Does that make sense? Yeah. Now from here, you are just integrating with respect to u. Treat it as if it is a dummy variable. It's 1/2 times, what is it? Integral of this one with respect to u? 1/8, right? U to the 8th plus c out there. So what is in simple form? 1/16 of u to the 8th, right? But what's u? U is here. U is originally x squared plus 3. So you put x squared plus 3 there and raise to 8th power and plus c. That's called substitution. Once you get used to the choosing, once you get good at choosing u, rest of the part is mechanical. And doing that. Common mistake is that if you make wrong substitution and you're left with some x not taken care of, and then pulling it outside and just integrate the u part all wrong, you might receive 0 if you do anything like that. You have to clearly understand this straightforward procedure. You have to write everything in terms of u. Good? All right. So, for example, if you do the third one, let's see if you remember this integral in here and derivative. What's the derivative of this one? This is d dx of x squared plus 2x plus 11 minus 1, right? If the numerator is not function, it's this exponential rule is better for the derivative. Even if there's something in there, you can write it as a times b, negative 1. If it is a over b integral, I think it's better, in my opinion. All right, so how do you differentiate this one? This is your u, right? So negative 1 comes down, x squared plus 2x plus 11. What happened to the power here? Negative 2, right? So what do we multiply? Derivative of u, right? So what is that? Yeah, 2x plus 2. So if you put that back in the denominator, that will be 2x plus 2 divided by x squared plus 2x plus 11 second power. And you will get the same answer like this if you use a quotient rule instead of this one in here. Does that make sense? All right, here's your exercise number 2. Is that right? So I'm going to hide this one and ask you to compute the antiderivative of this function. This is substitution rule. And think about what is the first thing you do. You make a choice of u, right? What is going to be my u? And then write down du dx. And after you write down du dx and you contemplate a little bit, is this a good choice or not? And if you think it's a good choice, then move on. Multiply the reciprocal of du dx and so on. I apologize, I'm running out of time, so I have to cut short here. My choice of u was the whole denominator. Then its derivative was 2x plus 2. Then if you factor out 2, you're left with x plus 1, and you realize that, oh, there's x plus 1, even though it suddenly looked different from 2x plus 2. So if I proceed with this with this choice of u, is reciprocal down there, will take care of this x plus 1. So you enter this simpler expression. That whole thing was u, right? So it is simply 1/2 of 1 over u, antiderivative 1 over u. That's ln. So if you substitute back, you get this answer. And if you try to differentiate this one and verify that derivative of this one is that, that's also easy. Okay? And down here I'm putting a little remark that x squared plus 2x plus 7 has a negative discriminant. That means it assumes always the same sign, positive or negative. And here, by completing the square, you can see this is always a positive number. So absolute value is unnecessary. But in general, you do have to put absolute value around quadratic. But this was a special quadratic expression, so that it never hits 0, so that is unnecessary in that case. Such as x squared plus 1. You know it never hits 0, right? Because square plus 1. So absolute value of x squared plus 1 is the same as x squared plus 1. Alright? I know some of you have learned this substitution.